Okay, so the success criteria is pretty straightforward, just the one today, and that is that I can find the volume of a solid that has been formed by rotating a curve about the x-axis. So I'll unpack that for you in a second so you can sort of see what we're talking about there. Now on the to the right of the data projector screen, that's the formula. There you go. Volume is equal to the integral from a to b of f of x squared dx, and we multiply the whole thing by pi. There we go. Now, that's just the formula. As a script monkey, you can probably just remember the formula and make sure you can try to apply it to different contexts. But I do want to spend some time just explaining how that formula is derived so that you understand where it's coming from. It's not too hard, although some of the workings out might be need to be taken a couple of steps at a time. So let me just pull out so that you can see all four shots at once there. And I'm just going to go to slide 2 now. So just a reminder that if we have a function and if we say take a starting point and an end point like so, is that bright? Is that okay? Is that clear enough for you? Yeah, I don't know if I can do much with the curtains though, is anything. If we find the integral between those 2 points, is that any better? A little bit. If we find the integral between those 2 points, the definite integral, we'll get the area under the curve. And we spent time last term describing that. And so first of all, we need to know the function. And this one is just meant to be f of x equals x squared. That's all. I haven't quite hit the 0 there in the middle there, but you get the idea. And so the integral becomes from of f of x dx between a and b, which would be in this case x squared, like so. I might just zoom up because it's probably just a bit too small. You don't really need to see the other slides at the moment. That's a bit better, isn't it? And so if we take some specific endpoints, like so, between 1 and 3, for example, then we would have, should remember the x, the integral between 3 and 1 of x squared dx. So we find the antiderivative of x squared, which is x cubed on 3, and we put our boundary values in like so, which we then substitute in. So that gives us what? 3 squared, so it gives us 9 minus a third, which is equal to 8 2/3, and that's the area under the curve. Is that okay? Just as a reminder about what we used to do for area, and that gave us that slice there, if you like. Good so far? That's just a reminder. Any questions? Okay, so what happens, you can see down there in slide 3, what happens if we rotate that area, and specifically if we rotate the area around the x-axis? It's going to be hard to actually demonstrate this really, so I've got a little animation to show you what I mean. But let's just say we take that little slice that we found the area of, and what we do is about the x-axis, we then rotate it around until it goes up to the top again. I'm going to show you a little animation which is based on a different curve, but it's the same idea really. And if I just loop it, you'll see what I mean. So we're going to look, this is looking at the area from 0 to 1 of this particular function here. Looks a bit exponentially kind of. And I'll just loop it. Oh, that's not looping very well. Let's hit the reset button. Okay, it was doing better than that before. Don't know what's going on. So you can sort of see it makes this sort of curvy kind of shape, like so. Okay, so this is rotating backwards. around and around and around, and it forms this kind of solid shape. Okay, it's almost cone-like in its dimensions there. Okay, so does that kind of make sense so far? That if we rotate a curve around the x-axis, it'll form this kind of solid shape. All right. So there we go. So that's point number one there, that it forms some sort of, it forms a solid shape. I know you can't see what I'm writing here. I'm going to switch over in a second. I should even get rid of the word shape. It forms a solid, like so. So the question is, how can we work out the volume of that solid that is created from rotating the curve around? Well, if I just go back to that same web page and scroll down a bit, if you remember what we did for integration, do you remember what we kind of did was when we were looking at how to work out area, we sort of split, oops, just want to use the pointer. We sort of split it into little rectangles, and we said, like, if we approximated by little rectangles, the curve by little rectangles, then by adding up those little areas, then we would get the area under the curve. And if we keep on making those little approximations closer and closer and closer and closer and closer and closer to the curve, then effectively the sum of the areas is effectively the sum, is the integral of the function. That's how we defined the area under a curve in the first place. So by splitting it into little rectangles, we're going to do the same thing for volume. So if we have a look at this second diagram here, we'll get a feel for that. So we can sort of approximate the volume by approximating the curve by these rectangles. And then if I curved these rectangles, if I rotated these rectangles around the x-axis, we would have a whole bunch of discs here. I'll try and see if this loop works a little bit more steady. No, it's a bit weird. This is technology 101. It works everywhere except for when you're actually presenting it. I might just try hitting the refresh button, see what happens. Come on, there we go. So I'll just slow it down a little bit. So you can see what's happening there, that each of those rectangles is a disc that's built up to form an approximation of the shape we saw above. And again, if we keep on taking thinner and thinner slices, we would get smaller and smaller discs. But when you add up all of those discs, it would end up being extraordinarily close to this shape here, which is formed. There it goes, rotating a little bit nicer now as well. Like so. Okay, so we continue to approximate it effectively. Right, good so far? Yep. Okay, so next thing to point out is when I say disc, what's another way we could describe each of those shapes there, each of those solids? Yeah, it's a cylinder, all right? So a cylinder has a height and a radius. What's the formula for the cylinder, for a cylinder? For the volume of a cylinder, sorry, and forgetting the important word of V. You don't remember? Pi times what? Okay, Ollie, thank you. Pi is absolutely correct for a start. We need more. Yeah. Pi r squared h, good. Okay, the idea there is that we have a cylinder of base, the base of a cylinder is a circle, so the area of the base is pi r squared. A cylinder is like a prism. It's not a prism, but it's like a prism in that it has the same cross section all the way through. So we multiply pi r squared by the height to get pi r squared h. Okay. So we are going to do a sort of a similar thing here. We are going to have a look at, let's go full screen now. Zoom up a little bit. we're going to have a look at this concept of what would a cylinder look like when we rotate it around. So if I sort of just have a look at our little curve here and just take a little section of it, just draw it in red. This is one of our little slices. Okay, then this distance here is that change in x value, isn't it? It's the change in x, which we normally use dx to describe. It's the change in x. So it's the distance from one x value and a little bit further along. So it's dx. Okay, so on a cylinder, that's kind of like the height. Now, as we rotate this cylinder around, so the cylinder, oh, this is going to be awful. Cylinder is going to go, so this rectangle is going to go around like that. As it goes around, then the radius of the cylinder is simply going to be given by the height of this rectangle. So that's the value of y. Is it okay so far? So for this little cross section, we have volume is equal to pi r squared h, but r is the value of y, so it's y squared, and h is the small change of x, so it's times dx. So it's pi y squared dx. Okay? So that's all right, except that that's only one tiny little slice. If we summed up all the rectangles there, we would get approximately the volume of the rotation. But we know that if we take the limit of that sum, then by integration, we will get the exact volume. Okay, that's probably the leap of faith that you need to sort of be on board for. Just like the integration of the integration of the function gave us the area under the curve, I'm saying the integration of this will give us the volume under the curve. Okay, so that leaves us with, I'll go to the black pen so you know that it's important. I'll just zoom out a little bit. So therefore, the volume of curve between A and B is V equals the integration or the integral between A and B of pi y squared dx. Okay, that's it. That's basically it. If you look at the right-hand side of the board there, what I've written there on the right-hand side is basically what I've written there. I'm going to just transform it now so that it's in the PDF notes as well. But do you remember that constants, and pi is a constant because it doesn't change values. Do you remember that constants can be taken outside the integral with no dramas? So that means we've got pi outside of B to A, and then y is simply the function. And so instead of writing y, I'm going to write f of x squared dx. And that's the formula for volume of the rotation about the x-axis. That's it. Any questions? Should we look at an example and then I'll let you loose on some problems? Okay, here we go. Nice, simple one. I'm going to zoom up so we've got a bit of space there. We have a straight line. I'm giving you a point, an end point for that line. When x equals 3, y equals 2. And I'm asking you to consider the rotation about the x-axis, or the volume of the solid formed when the function is rotated about the x-axis. Okay, first of all, we better have a look at the function itself. I'm going to give you a moment to draw the diagram and just write to the side of the diagram what the function is. It's linear, so there's no squares or cubes or anything like that. No tricks to it. I'll wait 30 seconds and then I'll just drip feed you a couple of hints, and then if you haven't got it after a minute or two, it'll be written anyway. So if you've got it straight away, don't worry about it. Don't have to wait long. You right, Louis? Da. Okay, so here's reminder number one. A linear function can always be written in the form of y, or f of x, equals mx plus c, where c is the y-intercept and m is the gradient. So if you can find m and c, you can write the function. C is the y-intercept. Remember, that is the value of y when x equals 0. So look at the sketch, look at where x equals 0. What's the y coordinate at that point? That'll give you the value of c. Oops. M is the gradient. Gradient, very basic definition of gradient, is rise over run. Rise is the change in y, the run is the change in x. How many units of y are changing for how many units of x? The coordinate that I've given you will tell you what that is. Okay, either you've got it or you haven't. No worries if you haven't, as long as you take some learning away from this, that you need to do some more work on making sure that you can model functions from a sketch diagram. So I'm going to use f of x notation. You could just have written y, that's fine. F of x is equal to mx, so I need m. So here, I can see at this point here, the graph has gone up for 2 units at the same time as it's gone across 3. So the gradient is 2 over 3. So it's 2/3 x, or 2x on 3 would be fine as well if you've written that. And then c is the y-intercept. I can see that it cuts through it at the origin. So the y-intercept is 0. So I don't need to write plus 0 in. And so the function is simply f of x equals 2/3 x. And that's it. So let's work out the volume. Volume is equal to pi integral between 0 and 3. That's my natural boundaries there. 3 because it's given to me, and 0 because it must be the other boundary. 2/3 x squared dot dx. That's equal to pi integral between 3 and 0 of 4/9 x squared dx. And now I'm going to take my constant value out so I don't have to confuse myself later on. That's equal to 4 pi on 9 integral between 3 and 0 of x squared dx. Okay, so I'm just left with x squared dx, and now I'm going to find the definite integral of that. So that's equal to 4 pi on 9 times x cubed on 3 between 3 and 0. That's equal to 4 pi on 9 outside of 3 cubed on 3. And I have to subtract the value when x is equal to 0. But when x is equal to 0, that whole thing is equal to 0. Did you say what? Okay, so I've substituted, I'll actually spell it out. I was going to just skip a step, but I won't. I've substituted the upper boundary for x to get 3 cubed minus 3. And now I will subtract the bottom boundary, like so, because that's how I do a definite integral, right? Top boundary substituted in minus bottom boundary substituted in. So I've done that, but is it okay? Can you see that that's just 0? So it's just 0 divided by 3. Okay, so that gives me 4 pi on 9 times by 3 cubed on 3. Now, I can do some cancelling down here, and if your fractions knowledge is a little bit weak, it's probably going to be a little bit of a struggle for you. But I'm going to take out 3, goes into 3 cubed, and that leaves me with 3 squared. And 3 squared is 9, so the 3 and the 9 cancels out. And so I'm left with 4 pi. Okay? Now, before I go any further, this is just a bit of an imagination thing, really. Just going to zoom out for a bit. Looking at that sketch, I didn't ask you to consider what solid was made, but we have a straight line here. What would happen if I rotated that straight line around the x-axis? What shape would I be left with? Ashley? Yep, it'd be a cone, right? Because I'd have nothing here when I rotate it. Then I'd have sort of concentric circles like so as I build it up. And that would, sorry, I've done a dodgy job there, but I just didn't want to get over my other writing. But I would have these concentric circles built up, so it would form a cone, because a cone has a straight edge for a slope, if you like. So it would be a cone. And the formula for a cone is, can anyone remember? A third pi r squared h, isn't it? Okay. So what would the radius of this cone be? 2. From here to here would be the radius. So it's got a radius of 2. And the height, would be here, because the cone's on its side. So the height would be 3 units long. And so if I use my cone formula, I've got a third pi times 2 squared times 3. So that'll be a third times pi times 4 times 3. I'm just going to put the 3 on 1 there to show you that this 3 and this 3 would cancel out. And that would leave me with 4 pi, just like we had in the slide above. Okay, so if I said here is a cone, it has height h and height 3 and radius 2. What is the volume of that cone? Then you would use the cone formula to determine that it is in fact 4 pi. That's the exact value of the area. And you can see that volume by integration does not disagree. That exactly the same, if I draw it as a formula effectively and then rotate it around to give me the same shape, then integration gives me the same value. So it's good to have that. And in fact, if we generalize this, rather than talking about 2/3, we talked about R and H. If we generalize this and integrated the generalization, we would in fact get a third pi r squared h, which is really cool. Okay, That's where I'm going to stop for a second. What's going to happen now is I'm going to let most of you, maybe all of you, I don't know, start working through your textbook work. I'll tell you what exercises in a second for the duration of the lesson. But I've got one extension example to consider. I don't want to say too much about it, but I'm going to work in general principles to prove a volume formula by integration. It's interesting. I like it. I think it's cool because it gives sense to some of the formulas that we just use mathematically almost. And I'm going to do it by looking at that extension example there, the square root of 2rx minus x squared. And I'm going to prove a volume formula based upon that. But you know what? You've got an example, you've got the theory behind it. If you're not keen to see that, that's fine, just get on with your bookwork. But if you are keen to see another more complicated example and you're up for that, then I'd encourage you to continue following on. It'll probably take me 10 more minutes or so. So for those of you, sorry, let me just say where to go to from here and then I'll let you go. So for those of you that just want to get on with it now, it's exercise 9M and 9N. So it's both exercises on page 319. You might want to skip a couple and to get through both of those exercises in the next half hour or so, but that's basically what we're going to be looking at. So I'll give people a chance to get into that. What do you need that's not in the textbook already, like with review work and stuff like that? I'll see what I can find. Right, so even if no one's going to pay attention to me, I'm going to speak as if everyone's listening because it might be useful for the notes for later. So, but I'll be as fast as I can. So the extension example looks at this funny old function here. It looks funny, but let's have a look at it on Desmos so that you can sort of see that it actually makes a shape that you're pretty familiar with. So the square root of 2rx minus x squared. But I'm going to just take it back to straightforward numbers to start with. I've got y equals the square root of 10x minus 2 minus x squared. And you'll see that it forms this shape here. And I have deliberately limited the function to the values between 0 and 10. Now that shape there, I'm hoping people can see that are paying attention, is a semicircle. Now, the semicircle has a radius of 5 and hence a total length of diameter of 10. Now, if you think about it, that's a semicircle, and if I rotated a semicircle around the x-axis, I would be left with a sphere. Okay, so I'd be left with a sphere, and the formula for a sphere is 4/3 pi r cubed. So I'll just switch back to the sketch notes. So I'll write that on the side. The volume of a sphere equals 4/3 pi r cubed. Sorry, I might have said squared before. 4/3 pi r cubed. So we're going to see how integration will in fact give us 4/3 pi r cubed. So in my example here, what makes it a little bit tricky, I suppose, is that I have deliberately left it general. Rather than saying 10x minus x squared, I've got 2rx minus x squared. So again, why 2r? Well, because the length is going to be the diameter. So rather than saying dx, I've just said 2rx instead. So instead of 10, I've got 2r. Okay, so that's all well and good. So if I wanted to work out the volume of that rotation, which remember would be a sphere, I would have volume is equal to pi between, now what values? It's going to be between 0 and, looking at this again, all the way across to 2r. Okay, in this case, the radius is 5, so it goes as far as 10. And so the rotation, so the integration is going to be between 0 and 2r. And then I've got a square root of the function 2rx minus x squared, which I'm then squaring, dx. So the handy thing about that is because I'm squaring a square root, it becomes a lot simpler. It simply becomes 2r, pi 2r and 0 of 2rx minus x squared dx, which is fairly straightforward to integrate. So we'll do that next, remembering that r is a constant value, so I don't need to increase the power of r or anything, I'm only looking at x. So that's equal to pi, and then we've got 2rx, so that becomes 2rx squared on 2 minus x cubed on 3, and that's between 0 and 2r. I'm going to zoom out a little bit now. Okay, so the rest of it is just trying to make sense of what all this means. I'm going to simplify as much as I can. So here, the 2's cancel out. Oops, wrong tool. The 2's cancel out, leaving me with rx squared minus x cubed on 3 between 2r and 0. Now I'm going to substitute in. So it's going to be r times 2r squared minus 2r cubed on 3. And then because I'm subtracting the lower boundary substituted in, then that x would be 0 and that x would be 0. So the whole thing would be 0. So I would effectively be subtracting 0. So I'm not going to include it. Just going to close off here. And now I'm just going to simplify the insides of the brackets. So I've got r times 4r squared minus 8r cubed over 3. Nearly there. So that's 4r cubed minus 8r cubed on 3. Okay, so I want to try and get a common denominator there. So the common denominator is 3. So that's 12r cubed over 3 minus 8r cubed over 3. And now I can subtract those numerators. So 12r cubed minus 8r cubed is 4r cubed. So I've got pi times 4r cubed on 3. And that, as a final line, just have to zoom out a little bit for you. As a final line is 4/3 pi r cubed, which is the volume formula that we first stated up here, 4/3 pi r cubed. So you can see that by integration, the formula for the volume of a sphere is able to be worked out. So there you go. So that's kind of neat, I thought, to see that in action, how the formula actually can be derived using more complex mathematics. Because otherwise, why is a sphere's volume 4/3 of pi r cubed? How does that work? You can sort of do it by looking at putting a sphere in a box and sort of saying, well, it's got 4/3 of the volume and stuff like that. But it's not as straightforward as that to conceptualize, I think. Whereas integration, although it's complicated, in fact, will give you the same result in logical steps. So there you go. That's it. I'm done.